What if I told you the universe isn't as empty as it seems, that every inch of space around you, even the air between your hands right now, is humming with an invisible energy so fundamental, it shapes everything we know? This is the world of quantum fields, the hidden fabric of reality itself. Think of them like an endless, unseen ocean, where particles are just ripples on the surface, and the deeper you dive, the stranger it gets. Today, we're venturing into that ocean to explore 30 of the most mind-bending theories about quantum fields, ideas that challenge our understanding of existence, from the tiniest particles to the vast expanse of the cosmos. Imagine standing at the edge of the known universe, peering into the void, only to realize the void isn't empty at all. Quantum fields are everywhere, filling what we once thought was nothingness with a complex dance of energy and potential. They're the reason particles pop in and out of existence, why light travels as both a wave and a particle, and perhaps even the key to unlocking the greatest mysteries of the cosmos. Some scientists believe these fields could hold answers to dark energy, the multiverse, or even the nature of time itself. And yet, despite their omnipresence, they remain one of the most elusive concepts in physics. This journey isn't just about abstract ideas, it's about redefining how we see reality. From theories suggesting quantum fields might be holographic projections to wild possibilities about alternate dimensions bleeding into our own, each of these 30 concepts will stretch your imagination. Whether you're a seasoned science enthusiast or just curious about the universe's deepest secrets, there's something here to make you pause and wonder. So let's dive in, because what you're about to discover might just change the way you see everything. Let's start with a theory so fundamental, it redefines what empty even means. Picture the vacuum of space, not just the black void between stars, but the space right in front of you. It's not empty. Instead, it's a seething, bubbling cauldron of energy called the zero-point field. Even at absolute zero, when all matter should theoretically stop moving, this field never rests. Tiny particles and antiparticles flicker in and out of existence like sparks in a cosmic fire, borrowing energy from nowhere and vanishing almost instantly. Scientists call this quantum foam, and it's not just theoretical. We've measured its effects in the lab. Now, here's where it gets wild. This restless energy might hold the key to one of the universe's biggest mysteries, dark energy. You see, the zero-point field could be the invisible force pushing the cosmos apart faster and faster, stretching galaxies away from each other like dots on an inflating balloon. But there's a twist. If you calculate how much energy this field should contain, the numbers are mind-boggling enough to rip the universe apart instantly. Yet somehow, reality stays intact. This glaring mismatch between theory and observation is called the vacuum catastrophe, and it's one of physics' greatest unsolved puzzles. Some researchers think the answer lies in hidden dimensions or undiscovered laws of nature. Others suggest we're seeing only a shadow of the true energy, like watching ripples on a pond without knowing the depth beneath. Whatever the solution, one thing's clear: the zero-point field isn't just background noise. It's a dynamic, writhing layer of reality that challenges everything we thought we knew about space, time, and the very fabric of existence. Now let's zoom way out, to a time when the entire universe was smaller than a single atom. In those first, unimaginably brief moments after the Big Bang, something extraordinary happened. Tiny quantum fluctuations, those same unpredictable ripples in the quantum fields we just discussed, got stretched to cosmic proportions. Picture blowing up a balloon with microscopic writing on it. The tiny scribbles expand into enormous patterns. That's essentially what happened when the universe underwent inflation, a period of faster-than-light expansion that lasted just a fraction of a second. Those minuscule quantum ripples became the seeds for everything we see today. denser regions packed with extra energy eventually collapsed under gravity to form galaxies, while emptier patches became the vast cosmic voids between them. It's a staggering thought. Every star, every planet, even the structure of the universe itself, might trace back to random flickers in a quantum field. But here's the kicker: we can actually see the evidence for this. The cosmic microwave background, the afterglow of the Big Bang, shows faint temperature variations, hot and cold spots, that match the pattern of those primordial quantum fluctuations. It's like finding the fingerprints of the quantum world stamped across the entire sky. Some theories suggest inflation wasn't a one-time event, but part of an endless cycle, with new universes bubbling into existence from quantum foam. Others propose that these fluctuations could reveal hidden dimensions or even alternate realities. Whether inflation was a singular cosmic accident or part of a grander multiverse, one thing is certain: those quantum whispers from the dawn of time shaped the universe we call home. The Higgs field is like the backstage manager of the universe, quietly pulling strings to give particles their weight. Think of it this way: imagine a room filled with paparazzi photographers. That's the Higgs field. Now picture a celebrity walking in. That's a particle. If it's an A-lister like an electron or quark, the paparazzi swarm around them, making it harder for them to move freely. That resistance is what we experience as mass. The more a particle interacts with the Higgs field, the more paparazzi it attracts, the heavier it becomes. Photons, on the other hand, are like invisible bystanders. They glide through untouched, which is why light has no mass at all. This isn't just a clever metaphor, it's a cornerstone of modern physics. In 2012, scientists at CERN Large Hadron Collider finally caught a glimpse of the elusive Higgs boson, the particle associated with this field. It was like finding the paparazzi's camera flash in a crowded room, proof the field exists. The discovery confirmed a 50-year-old theory and filled in a critical gap in the standard model of particle physics. Without the Higgs field, particles would zip around at the speed of light, never clumping together to form atoms, stars, or us. But here's the puzzling part: the Higgs boson is surprisingly lightweight compared to what many theories predicted. Some physicists think this weight problem hints at undiscovered particles or even parallel Higgs fields lurking in higher dimensions. Others suggest the value isn't random. It might be fine-tuned by some deeper cosmic principle we haven't uncovered yet. One thing's certain: the Higgs field isn't just a static backdrop. It's an active player in the universe's story, shaping everything from the tiniest particles to the largest structures in the cosmos. And there's another twist: the Higgs field might not always be stable. Some theories suggest it could temporarily exist in a higher energy state, like a pencil balanced on its tip. If it ever tipped over into a new state through a random quantum fluctuation or high-energy collision, it could rewrite the laws of physics in an instant, altering mass itself. The good news: if this happens, it would spread at the speed of light, meaning we'd never see it coming. The bad news: well, let's just say you wouldn't have time to worry about it. From giving particles their substance to potentially holding the universe's expiration date, the Higgs field is anything but ordinary. It's a reminder that even the most fundamental aspects of reality are teeming with unanswered questions and possibilities. Ever reach out to touch something only to realize your hand is miles away? That's essentially what happens with quantum entanglement, except the touching happens instantly, no matter the distance. Take two particles born from the same quantum event, and they become linked in a way that defies common sense. Change the spin of one, and its partner flips too immediately, as if they're sharing a secret faster than light could ever travel between them. Einstein famously called this spooky action at a distance, and for decades, physicists argued whether it was real or just a flaw in our understanding. Then came the Bell tests. These experiments, first proposed in the 1960s and refined over decades, closed every loophole skeptics could imagine. Scientists sent entangled particles flying in opposite directions, measuring their properties at distances so vast, even light wouldn't have time to relay a signal between them. The result, the particles behaved as one, coordinating instantly as if space between them didn't exist. It wasn't a glitch, it was a fundamental feature of reality. So how does this work? The answer might lie in the quantum fields themselves. Entangled particles could be like distant ripples on the same invisible pond, connected not by physical wires but by the underlying field that permeates everything. Some theories suggest entanglement reveals a deeper layer of reality where separation is an illusion, that at the quantum level, the universe is fundamentally non-local, with everything subtly intertwined. This isn't just philosophy. Quantum entanglement is the backbone of emerging technologies like quantum cryptography, where information can be secured in unhackable codes. Imagine sending a message where any eavesdropping attempt instantly breaks the entanglement, alerting both sender and receiver. Or consider quantum computers, which harness entangled particles to perform calculations that would take ordinary computers centuries. But here's the real mystery. If entanglement transcends space, could it also transcend time? Recent experiments suggest particles might become entangled after they've already been measured, as if the effect travels backward through time. Whether this hints at hidden dimensions, a holographic universe, or entirely new physics, one thing's certain: quantum entanglement forces us to rethink the very nature of connection in the cosmos. What if everything you see, the depth of a mountain, the curve of a planet, even the space between your fingertips, is just an illusion? That's the radical idea behind the holographic principle, a theory suggesting our three-dimensional universe might actually be a two-dimensional projection, like a cosmic hologram. Think of those shiny stickers that change images when you tilt them. At first glance, they seem three-dimensional, but peel one apart, and you'll find all that information is stored on a flat, two-dimensional surface. The holographic principle argues reality works the same way, that the universe's true code is written on a distant boundary, perhaps at the edge of a black hole or even the cosmic horizon, and what we experience is just a shimmering, three-dimensional decoding of that data. This isn't science fiction. The math actually checks out. In the 1990s, physicists studying black holes stumbled onto something bizarre. The maximum entropy, or information, a black hole can contain doesn't depend on its volume, but on the surface area of its event horizon. It's as if all the data about what's inside is compressed onto its two-dimensional surface, like a cosmic zip file. Extend that idea to the entire universe, and you get the holographic principle, a framework where all the information needed to describe every star, galaxy, and particle could be encoded on a distant, flat boundary we'll never see. Here's where it gets even stranger. If the holographic principle is true, it implies that space itself, the very fabric of distance and separation, isn't fundamental. It's emergent, like the pixels on a screen creating the illusion of movement. Just as a video game renders a three-dimensional world from two-dimensional code, the universe might render our reality from information stored elsewhere. This could explain some of physics' biggest puzzles, like why gravity seems so weak compared to other forces. It might not be a true force at all, but a side effect of the way information is projected. Critics argue the theory is untestable, but experiments are already in motion. Scientists have used quantum computers to simulate holographic universes, and gravitational wave detectors might someday spot subtle pixelation in spacetime itself. Whether the holographic principle holds up or not, it forces us to confront a humbling possibility. The richness of our three-dimensional world, the taste of fruit, the warmth of sunlight, the vastness of the night sky, might all be just the universe's most convincing mirage. We've mapped the cosmos with stunning precision, yet 85% of its matter is missing, not hiding, just invisible. This is the enigma of dark matter, a ghostly substance that bends light and sculpts galaxies without ever revealing itself. But what if it's not made of particles at all? What if dark matter is something far stranger, an invisible quantum field stretching across the universe, tugging on everything with the faintest gravitational whisper? Think of it like the Higgs field's elusive cousin. While the Higgs gives particles mass by interacting with them directly, this hypothetical dark matter field would barely interact at all. It wouldn't cling to atoms or reflect light. Instead, it would exist as a silent backdrop, warping space-time through gravity alone. Picture a vast, intangible net draped over the cosmos, its threads too fine to see but heavy enough to pull stars into orbit and glue clusters of galaxies together. The evidence for this idea lies in the way galaxies spin. Stars on the outskirts rotate just as fast as those near the center, defying gravity's usual rules unless some unseen mass is holding them in place. Traditional dark matter theories propose undiscovered particles, but quantum field alternatives offer a compelling twist. Instead of hunting for individual particles, we might be looking for a pervasive energy field, one so diffuse it slips through detectors unnoticed, leaving only gravitational ripples as clues. Here's where it gets even more intriguing. Some models suggest this field could have patches of higher density, like invisible reefs in the cosmic ocean. These dense regions might explain why dark matter seems clumped around galaxies, or why certain anomalies like the unexplained glow from distant neutron stars persist in our observations. If true, it would mean dark matter isn't just floating passively through space. It could have structure, dynamics, even waves, like the Higgs field's oscillations but on a galactic scale. Yet the biggest question remains: if this field exists, how do we prove it? Particle colliders hunt for dark matter by smashing atoms together, hoping to knock loose a hidden particle. But if dark matter is a field, we'd need subtler tools, perhaps gravitational wave detectors sensitive to the faintest tremors in space-time, or telescopes spotting distortions in ancient light. Either way, the search forces us to confront a humbling possibility. The universe's dominant form of matter might not be stuff we can touch, but an invisible current flowing through the quantum fabric of reality itself. Gravity is the cosmic rule-breaker, the one force that stubbornly refuses to play by quantum rules. While electromagnetism and the nuclear forces all bow to the strange laws of the quantum world, gravity operates on its own terms, warping space-time on a scale so vast it seems to laugh at the idea of tiny, discrete particles. This is the quantum gravity conundrum, a problem so deep it split physics into two incompatible worlds: the quantum realm, where particles flicker in and out of existence, and Einstein's general relativity, where planets and black holes bend the cosmos like a trampoline. Enter loop quantum gravity, one audacious attempt to fix this divide. Picture space-time not as a smooth, continuous fabric, but as a tapestry of tiny, interwoven loops, like a mesh of interconnected threads. These loops would be the smallest possible pixels of reality, far tinier than an atom, with gaps so small they're imperceptible at everyday scales. When you move your hand through the air, you're not gliding through empty space. You're passing through this intricate network, where each loop carries a quantum of area or volume. It's as if the universe has a built-in resolution limit, like a digital screen where you can't zoom in forever without hitting the pixels. But there's another contender: string theory. Instead of loops, this framework imagines all particles as minuscule, vibrating strings, each note in their hum corresponding to a different particle or force. Gravity, in this view, would be carried by a special string, the graviton, a hypothetical particle that's yet to be detected. String theory goes even further, proposing that these strings dance in a universe with not just 3 dimensions of space, but 10 or even 11, curled up so tightly we'll never perceive them directly. It's like ants crawling on a telephone wire. To them, it's a one-dimensional line, but to us, it's clearly a 3-dimensional cylinder. Why does this matter? Because without unifying gravity and quantum mechanics, our understanding of reality is incomplete. black holes, where gravity becomes extreme and quantum effects can't be ignored, are the ultimate testing grounds. Loop quantum gravity suggests that inside a black hole, space-time might not collapse into a singularity but instead rebound like a compressed spring. String theory, meanwhile, hints that black holes could be tangled knots of strings, their information encoded in ways we're only beginning to grasp. The challenge is that both theories are fiendishly hard to test. Detecting a graviton would require a particle collider the size of a galaxy, and observing spacetime's pixelation would need instruments sensitive to scales a billionth of a proton. Yet hints might lie in cosmic phenomena, perhaps in the faint echoes of gravitational waves or the way particles behave near the Big Bang's remnants. This isn't just academic. If either theory is right, it would rewrite our origin story. The Big Bang might not have been a singular explosion but a bounce from a previous universe or a higher dimensional collision we can't yet imagine. Time itself could emerge from these quantum knots, like temperature arising from the motion of atoms. One day, we might even harness these insights to manipulate gravity itself, not with sci-fi anti-gravity boots, but by understanding how spacetime's threads weave together at the deepest level. Until then, the quantum gravity conundrum remains physics' greatest unanswered call to adventure. There's a theory so unsettling it makes black holes look cozy, the idea that our universe might be built on a lie. Imagine standing on a frozen lake, confident the ice beneath you is solid. Now picture someone whispering that it's actually just a thin sheet, and deep below lurks an endless ocean of hotter, denser water. That's the essence of vacuum decay. According to this theory, the vacuum of space isn't truly empty or stable. It's a fragile, temporary state, like a soap bubble suspended in a far more stable environment. And if that bubble pops, the laws of physics as we know them could rewrite themselves in an instant. Here's how it works. Quantum fields aren't just idle backdrops, they have energy states like valleys in a vast cosmic landscape. Our universe sits in a shallow valley, the false vacuum, where fields have enough energy to sustain stars, atoms, and life as we know it. But there could be a deeper valley, a true vacuum where those fields would settle if given the chance. All it would take is one quantum fluctuation, one tiny nudge to push a patch of space over the edge. Like a spark in a dry forest, this bubble of true vacuum would expand at the speed of light, obliterating everything in its path. Atoms would unravel, forces would reconfigure, and reality as we understand it would cease to exist. The terrifying part, we wouldn't see it coming. One moment, everything's normal. The next, an invisible wall of redefined physics sweeps through the solar system, leaving no time to react. Distant galaxies could already be vanishing in this silent apocalypse, their light still traveling toward us, masking their fate until the instant the wave arrives. But here's where it gets even stranger. Some calculations suggest this might have already happened elsewhere. If a true vacuum bubble formed in some distant corner of the cosmos, its expansion could be so rapid that we'd never detect its approach. Other models propose that high-energy experiments, like those in particle colliders, could theoretically trigger such an event, though the odds are astronomically low. Yet there's a twist. Vacuum decay might not be the end. If the true vacuum's laws still permit some form of structure, a new universe could emerge from the wreckage, one with entirely different constants, forces, or dimensions. We'd never know, of course, but it raises a haunting question. Could our own universe be the aftermath of someone else's vacuum decay? For now, the theory remains speculative, a dark shadow at the edge of physics. But it forces us to confront an unnerving truth. The universe might not just be unpredictable. It could be fundamentally temporary, a house of cards waiting for the slightest quantum breeze to topple it all. What if the universe isn't just governed by quantum fields? What if it's running on them? The simulation hypothesis takes the strangeness of quantum mechanics and twists it into something even more provocative. the idea that our reality might be an advanced artificial construct with quantum fields acting as the underlying code. Think of it like a hyper-realistic video game where pixels are so small you can't see them except here. The pixels are Planck scale units, the smallest possible measurements of space and time. At this level, reality becomes grainy, as if the universe has a built-in resolution limit. Why would a perfectly smooth, natural reality have such a constraint unless it was programmed that way? Then there's quantum indeterminacy, the way particles exist in a haze of probabilities until observed, like a character in a game that only renders when you look at it. This observer effect could be interpreted as a cosmic optimization trick, a way for the simulation to save processing power by not calculating unobserved events in full detail. Even quantum entanglement's spooky coordination fits the analogy. Entangled particles might be linked not by hidden wires but by shared data pointers in the simulation's code, instantly updating each other's states without physical interaction. Elon Musk famously championed this idea, arguing the odds we're in base reality are astronomically low billions to one, given how quickly simulations could multiply in an advanced civilization. But skeptics point out glitches aren't proof, they could just reflect gaps in our understanding. After all, if the simulators wanted to hide their handiwork, why leave clues like Planck lengths or quantum uncertainty? Unless, of course, there are Easter eggs for us to find. The debate splits scientists. Some argue the simulation hypothesis is untestable metaphysics, while others propose ways to detect code artifacts, like anomalies in high-energy cosmic rays that might reveal the simulation's frame rate or pixelation. One physicist even suggested searching for mathematical symmetries that break down under extreme conditions, like rounding errors in a calculation. Whether you find the idea thrilling or unsettling, it forces a deeper question. If quantum fields are the substrate of reality, could they also be the substrate of someone else's design? Maybe the universe isn't just stranger than we imagine. It might be stranger than we can imagine, with quantum quirks as the closest thing we have to a backstage pass. What if your thoughts aren't just electrical signals? What if they're quantum symphonies playing out inside your brain? This is the provocative claim of quantum consciousness theories, which suggest that the strange rules governing particles might also govern our minds. At the heart of this idea are microtubules, tiny protein structures that act like scaffolding inside neurons. Most neuroscientists see them as mere cellular support beams, but a handful of researchers propose something far wilder, that these microscopic tubes could be quantum computers, processing information in ways classical physics can't explain. Enter Sir Roger Penrose, the Nobel Prize-winning physicist, and his Orch-or theory. He argues that consciousness arises from quantum vibrations inside microtubules, ripples of energy so delicate they'd collapse under the warm, wet chaos of the brain unless protected by some yet unknown physics. Imagine a pin balanced perfectly on its tip in a hurricane. That's how improbable quantum states seem in our noisy biology. Yet Penrose insists nature might have found a way, harnessing these fleeting quantum dances to generate self-awareness. Critics aren't convinced. They point out that quantum effects typically require extreme cold and isolation conditions utterly absent in the brain's messy, room temperature environment. Even photosynthesis, once thought to rely on quantum tricks, operates on far simpler principles than human cognition. Brain scans show no evidence of large-scale quantum activity, and opponents argue classical neuron firing explains consciousness just fine without invoking quantum mysteries. But here's the twist. Some lab experiments hint that microtubules might indeed exhibit quantum behavior. When exposed to certain frequencies, they vibrate in ways that resemble harmonic oscillators, systems known to sustain quantum coherence. It's faint, speculative evidence, but it keeps the door cracked open. Whether Orch-or holds up or not, it forces a thrilling question. Could the universe's deepest rules, the same ones that entangle particles and warp spacetime, also be the source of our inner world? If so, the line between mind and cosmos might be far thinner than we ever imagined. Ever opened a book and wished you could follow every possible storyline at once? That's essentially what the universe does according to the many worlds interpretation. Every time a quantum particle faces a choice, like whether to spin left or right, reality doesn't pick one option. It splits, creating two parallel worlds where each outcome happens. No collapsing probabilities, no single path, just an endless branching tree of universes, each one as real as the next. Take Schrödinger's infamous cat. In the classic thought experiment, the cat in the box is both alive and dead until you peek inside, forcing the system to choose. But many worlds flips the script. There's no superposition, no cosmic coin flip. Instead, the moment the box is sealed, reality divides. One universe where the cat purrs happily, another where it doesn't make it. Both exist simultaneously, forever separated by the branching of quantum fields. You just happen to experience one outcome, unaware of the other, you witnessing the alternate result. This isn't science fiction. The math behind quantum mechanics fully allows for this interpretation. When particles interact, their wave functions don't collapse, they entangle, weaving new threads into the fabric of reality. Imagine a hallway with infinite doors, each opening into a universe where every possible quantum event plays out. A version of you just scratched their nose in one, while another started a bakery in a timeline where they took that cooking class. The fields underpinning reality don't prune possibilities, they embrace them all. Critics argue this is extravagantly wasteful. Why would nature spawn countless universes just to accommodate every quantum whim? Proponents counter that it's actually the simplest explanation, stripping away the need for mysterious collapse mechanisms, and the implications are staggering. If many worlds is correct, there's a universe where dinosaurs never went extinct, one where your favorite band stayed together, even one where the laws of physics are subtly different. But here's the catch, these branches aren't reachable. They're like radio stations playing on frequencies you can't tune into, separated by quantum decoherence, a kind of cosmic static that prevents interference. Some theorists speculate advanced civilizations might find a way to hop between worlds, but for now, it's a one-way fractal of possibilities expanding faster than light. The real beauty of many worlds, it turns quantum weirdness into a feature, not a bug. The universe isn't indecisive, it's endlessly creative, and somewhere out there, another version of you is leaning in, equally fascinated by the very same idea. Time might feel like the most reliable constant in your life, ticking away second by second, never speeding up or slowing down. But what if it's just an illusion? A trick of the quantum world, that's the radical idea behind emergent time, a theory suggesting time isn't fundamental at all. Instead, it could be a side effect, a collective hallucination born from countless quantum interactions, much like temperature isn't a thing itself but a measure of how fast atoms are jiggling. Take a deep breath. The air you just inhaled is made of molecules moving in every direction, colliding chaotically. Individually, each collision is random, but zoom out and all that chaos averages into something we recognize as temperature. Now imagine the same principle applied to time. At the smallest scales, quantum events might not unfold in a neat sequence. Particles interact, entangle, and fluctuate without a clear before or after. But when you step back, all those messy quantum handshakes create the appearance of a smooth, flowing timeline. It's like watching a movie. The motion feels continuous, but it's really just thousands of still frames flashing by. Carlo Rovelli, one of the pioneers of this idea, compares it to a mountain seen through fog. From a distance, the peak looks solid and unchanging, but climb closer and you realize it's just a swirl of mist and rock with no fixed edges. Time in this view is the mountain, an emergent property that only makes sense when you're not looking too closely. The math supports this wild notion. Some quantum gravity equations, like those in loop quantum theory, work perfectly without time as a variable. They describe a universe where now is just a local agreement between particles, not a universal truth. Even Einstein hinted at this with relativity, showing clocks run at different speeds depending on gravity and motion. But emergent time takes it further. If time isn't woven into reality's fabric, the Big Bang wasn't a moment in time. It was the moment time itself crystallized into existence. So why does time feel so real? Think of a crowd at a concert. One person starts clapping, then another, and soon the whole audience falls into rhythm. There's no conductor, just emergent order from countless individual actions. Time could work the same way, with quantum processes synchronizing to create the arrow of time we experience. This might explain why entropy always increases, why eggs scramble but never unscramble, and why we remember the past but not the future. The implications are staggering. If time is emergent, the universe at its core might be timeless, a frozen network of quantum relationships where change is just an approximation. Black holes could be places where time melts back into this primordial soup, and quantum computers might one day reveal hints of a reality where cause and effect aren't set in stone. For now, the theory remains a beautiful, unsettling possibility, one that forces us to ask, if time is just a collective mirage, what else about reality might be too? Hold two mirrors perfectly parallel in empty space, and something bizarre happens. They're pulled together by an invisible force, as if the vacuum itself is pushing them. This is the Casimir effect, one of quantum field theory's most startling predictions proven real. At first glance, it defies intuition. How can nothingness exert pressure? The answer lies in the restless quantum fields we've been exploring. Even in a vacuum, these fields are never truly quiet. Virtual particles flicker in and out of existence, creating a sea of fluctuating energy. But when you place two plates extremely close together, closer than a hair's width, something changes. The plates act like walls, restricting which wavelengths of quantum fluctuations can fit between them. Outside the plates, all wavelengths are possible, but inside, only certain sizes fit. This imbalance creates a pressure difference, with more virtual particles pushing inward than outward. The result, the plates slam together with measurable force, as recorded in labs worldwide. It's like standing in a crowded room where everyone's randomly shifting positions except two people are pinned against a wall, unable to move. The chaos around them generates a net push they can't resist. Now, here's where it gets cosmic. The energy density between those plates isn't just lower than the surrounding vacuum, it's negative. That's right, the Casimir effect suggests regions of space can have less energy than absolute nothingness. A concept that sounds like science fiction but has been verified experimentally. And this negative energy isn't just a curiosity, it might hold the key to bending spacetime itself. Theoretical warp drives, like the Alcubierre model, rely on negative energy to compress spacetime in front of a ship and expand it behind, creating a bubble that could, in principle, move faster than light without breaking relativity. The Casimir effect proves such energy isn't purely hypothetical. Of course, the amounts we've measured are microscopic. Warp drives would need quantities far beyond our current grasp. But the door is cracked open. Skeptics argue that harnessing this effect for propulsion is like trying to power a rocket with static electricity. Yet breakthroughs in metamaterials and quantum engineering keep the dream alive. Some labs are already experimenting with layered nanostructures to amplify Casimir forces, while others explore whether negative energy could stabilize wormholes, those hypothetical shortcuts through spacetime. The deeper lesson here, quantum fields don't just fill empty space, they redefine it. What we call a vacuum is a dynamic arena of energy and pressure, where even nothing can push, pull, and potentially warp the fabric of reality. The Casimir effect is a tiny window into that hidden world, one where the line between impossible and inevitable is thinner than the gap between those two plates. Black holes were supposed to be the universe's perfect prisons, places where gravity is so strong, not even light can escape. But what if crossing the event horizon isn't a quiet plunge into darkness? What if it's more like hitting a wall of fire, a searing quantum barrier that burns you to ashes before you ever reach the singularity? This is the terrifying possibility raised by the Amps paradox, a puzzle so contentious it's divided physicists into warring camps. The story starts with Stephen Hawking's greatest insight: black holes aren't completely black. Thanks to quantum fields near the event horizon, they slowly leak radiation particles born from the vacuum's fluctuations, where one escapes while its entangled partner falls in. Over eons, this Hawking radiation causes black holes to evaporate, vanishing without a trace. But here's the problem. Quantum mechanics insists information can't be destroyed, yet Hawking's math suggested it was a contradiction that sparked decades of debate. Enter the Amps trio: physicists Olmary, Marolf, Polchinski, and Sully, who in 2012 proposed a brutal solution. If information must be preserved, then the entangled particles outside the black hole can't remain linked to their fallen twins inside. Something has to sever that connection violently at the horizon, releasing the energy as an incandescent firewall. Picture jumping into a black hole expecting darkness, only to smash into a plank-length thick wall of particles with the energy of 1 billion nuclear bombs. It's not just lethal, it shatters Einstein's vision of smooth, continuous spacetime. Hawking's original radiation, by contrast, was gentle, a slow trickle of particles that carried no fiery drama. The firewall idea horrified many physicists because it defied general relativity's core principle. Free fall should feel like floating, not burning. If firewalls are real, they'd mark the event horizon as a literal boundary, not just a point of no return. So how do we resolve this? One camp argues the firewall is a signal that quantum mechanics and gravity are fundamentally incompatible near black holes, a crisis pointing to deeper physics. Others propose exotic fixes, like fuzzball string theory's alternative, where black holes are tangled knots of energy without singularities or sharp horizons. There's even the wild AR equals EPR conjecture, suggesting entangled particles might be connected by microscopic wormholes, preserving information without firewalls. The stakes couldn't be higher. If firewalls exist, they'd rewrite our understanding of spacetime's fabric. If they don't, we're left grappling with how information escapes a black hole unscathed. Either way, the paradox reveals something profound. Quantum fields don't just fill space, they might also guard its most forbidden gates, turning the universe's darkest corners into cosmic minefields. Every particle you've ever heard of, electrons, quarks, even the Higgs boson, might have a hidden twin. That's the bold promise of supersymmetry, or SUSY, a theory so elegant it could solve half of physics' biggest puzzles in one stroke. Picture a cosmic mirror where every known particle reflects back as a heavier, more exotic counterpart. Electrons paired with selectrons, quarks with squarks, and photons with photinos. These shadowy superpartners aren't just theoretical window dressing. They could be the missing pieces of dark matter, the glue holding galaxies together while remaining utterly invisible to our detectors. Here's why SUSY matters. The standard model, our current rulebook for particles, is brilliant but incomplete. It can't explain gravity's weakness compared to other forces, or why the Higgs boson is improbably lightweight. SUSY smooths these rough edges by balancing the quantum equations. Each superpartner cancels out its twin's quirks, like counterweights on a cosmic scale. Even more tantalizing, the lightest superpartner, often the neutralino, wouldn't decay or interact with light, making it a perfect candidate for dark matter's elusive identity. The hunt for these particles has been anything but easy. For decades, physicists at the Large Hadron Collider have smashed protons together at near light speeds, hoping to spot superpartners in the debris. So far, nothing definitive, but that doesn't mean SUSY is dead. The theory is flexible superpartners might simply be heavier than we thought, hiding just beyond our current energy reach. Imagine searching for a whisper in a hurricane. Upgrading the LHC could turn up the volume enough to hear. Skeptics argue SUSY is a beautiful idea in search of evidence, a theory of anything that adjusts its predictions to dodge experiments. Yet optimists point to subtle anomalies, unexplained energy signatures in collider data, or cosmic ray patterns that don't quite fit the standard model. Whether SUSY is confirmed or refuted, its legacy is secure. It's pushed physics to ask deeper questions about symmetry's role in shaping the universe. And if superpartners are real, the implications would ripple far beyond dark matter. SUSY suggests space might have extra dimensions curled up like microscopic origami, and that the four fundamental forces were once united as one. It's a vision of reality where every particle, every force, every law is part of a grander symmetry, one we're only beginning to glimpse. Back in 1928, physicist Paul Dirac wrote down an equation that should have made perfect sense, but instead, it seemed to predict a universe teeming with impossible particles. His math described electrons with elegant precision, but it also demanded the existence of their bizarre twins, identical in mass but with opposite charge. These anti-electrons weren't just theoretical quirks, they were solutions to the equation staring back at him, undeniable yet utterly confounding. Where would such particles even come from? Dirac's radical answer: they're already here, everywhere. He proposed that what we call empty space isn't empty at all. It's a vast, invisible ocean, the Dirac Sea, where every possible electron state is already occupied, packed so densely that no real electron can move without bumping into another. Normally, this sea is perfectly uniform, undetectable. But if you inject enough energy to knock an electron loose, it leaves behind a gap in the sea, a hole that behaves exactly like a positively charged electron. That hole is antimatter. Think of it like bubbles rising in a glass of soda. The liquid is the Dirac Sea, and the bubbles aren't independent objects, they're absences where liquid once was. In this analogy, the bubbles are positrons, antimatter counterparts to electrons. Dirac's idea was poetic but initially dismissed as pure mathematical fantasy. Then, just 4 years later, Carl Anderson spotted positrons zipping through cosmic rays, their tracks curving the wrong way in a magnetic field. The universe had confirmed Dirac's madness. Today, we understand this through quantum field theory's lens. The Dirac Sea isn't literal, it's a metaphor for the quantum vacuum's restless energy. What Dirac called holes are actually excitations in the electron field, regions where the field's usual hum dips below its baseline. Antimatter isn't just the absence of matter, it's a mirror image, a ripple in the opposite direction. When matter and antimatter meet, they annihilate not because they're opposites, but because they're complementary. Filling the hole restores equilibrium, releasing energy like a snapped rubber band. Yet mysteries remain. If the Big Bang created equal parts matter and antimatter, why is the universe dominated by matter? Shouldn't everything have annihilated long ago? Some theories suggest subtle asymmetries in quantum fields might have favored matter's survival. Perhaps the same fields that birthed antimatter also doomed it to near extinction. Whatever the answer, Dirac Sea reminds us that even emptiness is alive with potential. Its depths hiding particles, energy, and perhaps the very reason we exist at all. Ever wondered why we all see the same world when quantum mechanics insists reality is a haze of possibilities? This is the puzzle quantum Darwinism tackles: the idea that what we call objective reality isn't handed to us on a silver platter. It's sculpted by a ruthless selection process where only the most stable, shareable quantum states survive. Picture a forest where countless seeds are scattered, but only the sturdiest trees grow tall enough for everyone to notice. That's how quantum states compete for dominance in our shared experience. At the quantum level, particles exist in superpositions, a blur of maybes, where an electron isn't strictly here or there until measured. But here's the twist: when quantum systems interact with their environment, they don't just collapse randomly. Certain states are more resilient, more prone to leaving imprints on the world around them. A photon bouncing off an object doesn't just carry information about one possible state, it carries echoes of the most stable state, the one least likely to be disrupted by further interactions. Over time, these robust states get copied and recopied, like a meme spreading across the internet, until they become the consensus version of reality. Think of it like natural selection for facts. Imagine a room with a chair in it. Quantum physics says the chair could, in principle, exist in many positions at once. But the chair's quantum states constantly interact with air molecules, light particles, and even your gaze. Most of those possible states are fragile. They decohere instantly, vanishing like soap bubbles. But the state where the chair sits solidly on the floor, that one gets reinforced trillions of times as photons scatter off it and air molecules jostle its atom. By the time your brain processes the scene, only the chair on the floor state has survived the quantum competition. This isn't just philosophy. Lab experiments with quantum dots and other tiny systems show how environmental interactions weed out fragile states, leaving behind the classics we recognize. It's why we all agree the moon exists even when no one's looking. Its quantum states have been broadcast and replicated so exhaustively by cosmic radiation, gravitational waves, and stray atoms that they've become objective. Critics argue this pushes the measurement problem into the environment. Why should interactions choose certain states? Proponents counter that it's not a choice, but an inevitability of statistics, like how air molecules tend to spread evenly in a room. The real magic lies in what this means for perception. Your consciousness isn't collapsing quantum waves, it's reading a universe-sized bulletin board where only the most persistent messages remain pinned. Quantum Darwinism doesn't just explain reality's solidity, it hints at something deeper. If our classical world emerges from quantum selection, might other consensus realities exist in parallel, shaped by different environmental pressures? Could aliens in a plasma-rich star system perceive a subtly different version of the same quantum substrate? The theory doesn't just answer questions, it opens doors to a cosmos where reality itself is a collaborative artwork painted by countless quantum brushes. Deep in the heart of quantum theory lies a puzzle so stubborn, it's survived every attempt to crack it: the strong CP problem. It's a glitch in the equations governing the strong nuclear force, the glue holding atomic nuclei together. The math says this force should break a fundamental symmetry between matter and antimatter, warping neutrons in a way we'd easily detect. Yet every experiment shows neutrons perfectly symmetrical, as if the universe quietly fixed its own math error. Enter actions: hypothetical particles born from an elegant solution to this riddle, and now leading candidates for dark matter itself. Imagine actions as cosmic whispers, vibrations in a hidden quantum field that permeates the universe. To understand why they might solve both puzzles, picture a crowded stadium doing the wave. Each fan stands and sits in sequence, creating a ripple moving through the crowd. Now shrink that down to quantum scales. The fans are the field's energy states, and the wave is an action. This ripple isn't just mathematical poetry. It's a tangible disturbance that could subtly tweak the strong force's behavior, canceling out the expected symmetry violation like noise canceling headphones silencing a hum. But here's where it gets even more intriguing. Actions, if they exist, would be extraordinarily shy, rarely interacting with normal matter, drifting through walls and planets like ghosts. Their sheer abundance could make them dark matter, clustering around galaxies in vast, invisible clouds. Unlike other dark matter candidates, actions wouldn't need to be massive. They could be billions of times lighter than electrons, yet so numerous that their combined gravity shapes the cosmos. detecting these phantoms is a challenge bordering on art. Since actions barely interact with anything, physicists have to get creative. One approach uses strong magnetic fields to coax actions into transforming into microwaves, like shaking an invisible tree hoping fruit falls into a detector. Experiments like ADMS are doing just that, tuning their instruments like cosmic radios searching for the faintest station. Yet the action story might be deeper still. Some theories suggest these particles aren't just passive spectators, they could form bizarre, galaxy-spanning structures called Bose-Einstein condensates, where actions act as a single quantum wave. Picture an ocean where every drop moves in perfect unison, creating currents on scales we can barely fathom. If true, dark matter wouldn't just be invisible mass, it might be a quantum fluid sculpting the universe in ways we're only beginning to guess. From fixing a quantum typo to potentially dominating the cosmos, actions remind us that the smallest solutions can have the grandest consequences. Whether they're out there or not, their legacy is already written in the equations that demand them and the mysteries they might yet solve. Einstein's two greatest seeming contradictions might actually be two sides of the same cosmic coin. In 1935, he and Nathan Rosen published a paper theorizing bridges through space-time wormholes, later dubbed Einstein-Rosen or ER bridges. That same year, with Podolsky and Rosen, he penned another paper railing against quantum entanglement's spooky action, now called EPR correlations. For decades, these ideas lived in separate worlds, one in general relativity's warped spacetime, the other in quantum mechanics' ghostly connections. But what if they're secretly the same phenomenon? That's the audacious claim of ER equals EPR, a theory suggesting entangled particles might be joined by microscopic wormholes, threads stitching the universe together at its deepest level. Picture two electrons born from the same quantum event, instantly entangled no matter how far apart they drift. Normally, we'd say they're linked by some invisible quantum thread. But ER equals EPR proposes something wilder, that beneath the math there's a physical bridge, a wormhole too tiny to traverse but real enough to transmit their synchronized states. It's as if space itself has hidden seams, and quantum fields are the needlework pulling them tight. The theory gained traction when physicists studying black holes noticed eerie parallels. Hawking radiation, the slow leak of particles from a black hole, involves pairs where one escapes while its twin falls in. Standard quantum theory says these twins are entangled. But if ER equals EPR is right, they're also connected by a wormhole, a tunnel through the black hole's interior. Suddenly, entanglement isn't just abstract correlation. It's geometry. This isn't just poetic imagery. The equations describing entangled particles and wormholes share uncanny similarities, as if nature's hinting at a deeper unity. String theorists like Juan Maldacena and Leonard Susskind have shown how, in certain models, manipulating entangled particles could literally create a traversable wormhole. It's like discovering that two unrelated keys you've been carrying for years actually fit the same lock, one unlocking spacetime structure, the other quantum weirdness. Skeptics point out these models rely on idealized scenarios like higher dimensional universes or perfect black holes, yet labs are already testing scaled-down versions. Quantum computers can simulate wormhole dynamics using entangled qubits, and tabletop experiments with graphene sheets mimic exotic spacetime geometries. While we're far from building stargates, each result nudges us closer to a revolutionary idea. Quantum fields might not just fill space, they could be actively knitting it together, one entangled thread at a time. The implications stagger. If every entangled pair is joined by a Planck-scale wormhole, the universe could be a vast network of hidden tunnels with quantum fields as the architects. Dark matter's gravitational grip might emerge from these subatomic stitches, and the Big Bang's singularity could be a cosmic knot where all threads converge. Even time's arrow might trace back to how these connections unravel. ER equals EPR doesn't just bridge two theories, it weaves them into a tapestry where space-time, matter, and quantum magic are threads of the same grand design. Whether the math holds or not, it reminds us that reality's deepest layers might be stranger than fiction, hiding connections where we least expect them. The very first moments of the universe weren't just hot and dense, they were a quantum roller coaster, with fields we can barely imagine dictating the fate of everything. Picture this: less than a trillionth of a second after the Big Bang, a mysterious field called the inflaton dominated reality. Unlike the familiar Higgs field that gives particles mass, the inflaton was a cosmic overachiever. Its energy didn't just fill space, it stretched it, ballooning the universe from smaller than a proton to something astronomically vast in the blink of an eye. This was cosmic inflation, and its fingerprints are still visible today in the afterglow of creation itself. Here's how it worked. The inflaton field wasn't perfectly uniform. Like a pot of water just before it boils, it had tiny quantum fluctuations, random ripples in energy that got magnified to cosmic proportions as space expanded. These minuscule jitters became the seeds for all structure in the universe. Denser regions eventually collapsed into galaxies, while emptier patches stretched into the voids between them. It's staggering to think that every star, every planet, even the web of galactic superclusters, might trace back to quantum tremors in this primordial field. But how do we know this actually happened? The cosmic microwave background, or CMB, is our time capsule from this era. When the Planck satellite mapped its faint temperature variations, it wasn't just capturing static, it was photographing the quantum noise of the infant universe frozen in time. Those subtle hot and cold spots, they're direct imprints of the inflaton's quantum fluctuations, stretched across the sky like shadows on a cosmic curtain. The data matches theoretical predictions with eerie precision, as if the universe left us a receipt from its first shopping spree. What's even wilder is that inflation might not have been a one-and-done event. Some theories suggest our universe is just one bubble in a frothing multiverse, where new inflating regions constantly bud off from quantum foam. Others speculate that the inflaton field could still be lurking in some hidden form, its energy woven into the fabric of dark energy, or even waiting to trigger a new phase of expansion. For all its success, inflation theory isn't without controversy. Critics point out we've never directly detected the inflaton particle, and the theory's flexibility makes it hard to falsify. But whether inflation stands the test of time or gets replaced by something even stranger, one thing's certain: those first quantum ticks of the cosmic clock set the stage for everything we see and everything we don't. The universe didn't just begin with a bang. It began with a quantum whisper written in fields we're only beginning to decode. What if heat itself is just an illusion, not a property of the universe, but a trick of perspective? That's the unsettling premise of the unravels effect, a quantum quirk where motion through empty space can literally conjure fire. Picture an astronaut floating in the vacuum, their engines dormant. To them, space is cold and empty, just as physics predicts, but now imagine they hit the throttle, accelerating faster and faster. Suddenly, their sensors start pinging, not with starlight, but with heat. A ghostly glow of particles appears where there was nothing before, as if the void itself has ignited. According to quantum field theory, that's exactly what happens. This isn't science fiction, it's a direct consequence of how quantum fields interact with relativity. When you accelerate through space, you're not just moving past objects, you're warping your own perception of reality's fabric. The quantum vacuum, which seems calm to a stationary observer, becomes a storm of virtual particles for someone accelerating. These particles aren't hallucinations. They're as real as the warmth from a campfire, with one crucial difference: their existence depends entirely on how fast you're pushing forward. The key lies in something called the Rindler horizon. Just as a black hole's event horizon hides events from observers outside, an accelerating spacecraft creates its own subjective horizon, a boundary beyond which light can never catch up. Virtual particle pairs constantly flicker into existence near this horizon, but now acceleration rips them apart. One particle falls behind the horizon, forever lost, while the other gets boosted into reality as detectable radiation. The result, a thermal bath of particles with a temperature directly tied to acceleration. Floor the throttle hard enough, and the vacuum around you could theoretically blaze at thousands of degrees. Here's where it gets even stranger. The unrun effect suggests that temperature isn't an absolute property of the universe, but a relative experience, like the pitch of a siren changing as it speeds past you. A fish swimming through water doesn't feel wet, and a stationary observer doesn't feel quantum heat, but start moving violently enough, and the universe responds by turning up the thermostat. This blurs the line between thermodynamics and relativity in ways Einstein himself might have found dizzying. Lab experiments can't yet reach the accelerations needed to observe unreal radiation directly we'd need to approach near light speeds within microseconds. But clever simulations using ultra-cold atoms or lasers mimicking accelerating frames have hinted at the effect's reality, and the implications are profound. If acceleration creates particles from emptiness, could the same principle explain the heat of black holes? Hawking radiation, the glow that slowly evaporates black holes, shares eerie similarities with Unruh's math, hinting that both phenomena might stem from the same quantum field gymnastics. Whether probing the birth of particles in empty space or redefining what heat even means, the Unruh effect forces us to confront a radical idea. Reality's rules might not be written in stone, but in the fine print of how we move through the cosmos. Somewhere between relativity's warped space-time and quantum field's restless churn, the universe keeps rewriting its own playbook, one accelerated observer at a time. Take a deep breath. The air you just inhaled contains trillions of molecules bouncing around in chaotic motion, an ordinary example of random fluctuations. Now scale that up to cosmic proportions where quantum fields flicker with even more dramatic unpredictability. Given enough time, not just billions or trillions of years, but timelines so vast they make the age of our universe look like a blink, could those fluctuations spontaneously assemble something unimaginable? Not just a particle or an atom, but an entire self-aware mind, complete with false memories of a life that never existed. This is the Boltzmann brain paradox, a thought experiment so unnerving it challenges our most basic assumptions about reality and consciousness. The idea traces back to Ludwig Boltzmann, the 19th century physicist who linked disorder to entropy. He realized that in an infinite, chaotic universe, even the most improbable events must happen eventually, including the random assembly of complex structures. Fast forward to quantum field theory, where empty space isn't truly empty but a seething foam of virtual particles. Given enough time, couldn't that foam briefly congeal into a functioning brain? Not attached to a body, not born from evolution, but a lone, thinking entity popping into existence from pure quantum noise, convinced it's a person living in a real world. Here's where cosmology throws gas on the fire. If the universe continues expanding indefinitely, as dark energy suggests, eventually all stars will burn out, black holes will evaporate, and space will approach absolute zero, a state called heat death. In that frozen eternity, quantum fluctuations become the only game in town. Statistically, over infinite time, the emergence of a Boltzmann brain would actually be more likely than the gradual evolution of life as we know it. After all, assembling one self-aware moment requires far less energy than crafting an entire universe's worth of galaxies, planets, and ecosystems. This leads to a bizarre conclusion. If Boltzmann brains are possible, then statistically, you are probably one. The countless disembodied minds flickering in the void would vastly outnumber real observers like us, making it absurdly improbable that we're the product of cosmic history rather than quantum accident. Your memories, your sense of self, even the device you're using right now, all could be a transient hallucination woven from random field fluctuations, destined to dissolve back into chaos as quickly as it appeared. Physicists recoil from this idea not because it's disturbing, but because it undermines scientific reasoning itself. If we can't trust that our observations reflect reality, how can we trust any cosmological model? Some theorists argue this paradox reveals flaws in our assumptions about the far future, suggesting the universe might cycle through rebirths or that quantum gravity prevents such fluctuations. Others propose that the mere fact we're having this debate is evidence against Boltzmann brains. If they dominated reality, coherent, stable thoughts like these would be vanishingly rare. Yet the paradox lingers, a ghost in the machinery of physics. It forces us to confront how little we truly understand about consciousness, probability, and the deep interplay between quantum fields and the arrow of time. Whether a chilling inevitability or a flawed thought experiment, the Boltzmann brain reminds us that in a universe governed by randomness, even existence itself might hang by the thinnest of quantum threads. Time's relentless march forward feels as certain as gravity. Eggs crack but never uncrack, coffee cools but never reheats itself, memories pile up but never unravel. Yet the fundamental laws of physics don't actually care which way time flows. Equations work just as well backward as forward, so why does time have an arrow at all? The answer might lie in the chaotic dance of quantum fields and a concept called decoherence, a process so pervasive. It turns the microscopic blur of quantum possibilities into the crisp, one-way flow of everyday experience. Picture a drop of dye swirling in a glass of water. At first, the dye forms a concentrated blob, its molecules neatly ordered. But give it a few seconds and those molecules begin to wander, colliding with water molecules until the dye spreads evenly. This is entropy in action, the universe's tendency toward disorder. Now imagine reversing the process. Every water molecule would need to move in perfect sync to herd the dye back into its original drop. The odds of that happening naturally are astronomically low. That's why time feels irreversible, not because the laws of physics forbid rewinding, but because the universe favors messiness over neatness. Quantum fields amplify this effect. At the smallest scales, particles exist in superpositions, multiple states at once, until they interact with their environment. A single electron might spin both up and down, but the moment it bumps into another particle, that fragile superposition collapses into a definite state. This is decoherence, and it's like the dye dispersing in water. Once the quantum system interacts with the outside world, there's no going back. The information about its original state gets scrambled into the environment, lost in a sea of quantum noise. But here's the twist. Decoherence doesn't just explain why quantum weirdness fades. It also explains why time's arrow emerges. Every interaction between particles, every measurement, every collision spreads information irreversibly, like ripples in a pond. You can't unscramble an egg because the quantum states of its molecules have decohered into the environment, their original configurations erased by countless interactions with air, heat, and light. The universe doesn't remember how to put Humpty Dumpty back together. Some theories take this further. If quantum fields underpin reality, then the arrow of time might not be fundamental. It could be an illusion born from our limited perspective. From a cosmic viewpoint, the entire universe might be in a single, timeless quantum state. But within that state, our experience of time emerges as quantum systems continuously decohere, locking us into a narrative that only flows one way. This isn't just philosophy. Labs studying quantum computers see decoherence in action. Qubits lose their magic when exposed to noise, forcing engineers to shield them at near absolute zero. Even black holes, those ultimate entropy machines, might owe their time-twisting properties to quantum information getting scrambled at their event horizons. So the next time you watch steam rise from your coffee, remember, you're not just seeing heat dissipate, you're witnessing quantum fields weaving time's arrow into reality itself, one irreversible interaction at a time. Imagine a universe where everything you see, every star, every atom, even the space between them, is actually a projection from a reality with one fewer dimension. That's the essence of the AD/S/CFT correspondence, a radical idea that ties together two seemingly unrelated branches of physics: gravity in higher dimensions and quantum field theory in lower ones. Picture a hologram on your credit card. The flat, shiny surface encodes a three-dimensional image. Now scale that up to cosmic proportions. According to this theory, our four-dimensional spacetime, with its warped gravity and swirling galaxies, might just be the holographic shadow of a five-dimensional world we can't perceive. The math behind this is as elegant as it is mind-bending. In the late 1990s, physicist Juan Maldacena discovered that a particular type of higher-dimensional universe, a warped space known as anti-de Sitter space, or AD-S, could be perfectly described by a lower-dimensional quantum field theory living on its boundary. This boundary theory, called a conformal field theory or CFT, doesn't include gravity at all. Yet somehow, the gravitational interactions in the higher dimensional bulk emerge from the quantum dance happening on the lower dimensional edge. It's as if the script for a Shakespearean play, written in plain English, could magically transform into a three-dimensional performance complete with sets and actors just by being read aloud. String theory plays a starring role here. In the higher dimensional AD-S space, gravity is described by strings vibrating in extra dimensions. But on the lower dimensional boundary, those strings translate into quantum particles interacting without gravity's influence. The duality suggests that gravity might not be a fundamental force at all. It could be an emergent phenomenon, a side effect of how quantum information is scrambled and encoded at the universe's edges. Visualizing this requires some mental gymnastics. Think of a fishbowl where the fish represent particles in the higher dimensional gravity-filled world. Now imagine that every movement of the fish is perfectly mirrored by ripples on the surface of the water. Those ripples are the quantum field theory on the boundary. The fishbowl's depth isn't an illusion, but its behavior is entirely determined by the two-dimensional activity on its surface. The implications are staggering. If AD-S/CFT holds, it could revolutionize how we understand black holes. The information paradox, where black holes seem to destroy information, violating quantum rules, might dissolve if the hole's interior is holographically encoded on its event horizon. Even more provocatively, some theorists suggest our own universe might be a boundary projection of a higher dimensional reality, with dark energy or other mysteries tracing back to that hidden layer. Critics point out that anti-de Sitter space is an idealized mathematical playground, unlike our universe's observed de Sitter expansion. Yet experiments with quantum computers are already simulating simplified versions of this duality, and unexpected connections keep emerging, like how entangled qubits might correspond to wormholes in the higher dimensional picture. Whether AD-S/CFT is the final word or just a stepping stone, it forces us to confront a profound truth. The universe's deepest secrets might not be hidden in the fabric of spacetime, but in the quantum codes written at its edges. Dark energy isn't just some vague cosmic force. It might be a quantum field with a sinister agenda, one that could rewrite the universe's final chapter in the most violent way imaginable. Right now, it's gently pushing galaxies apart, but what if it's slowly gaining strength? This is the chilling premise of phantom fields, hypothetical quantum fields where dark energy doesn't just persist, it grows exponentially, like a runaway freight train with no brakes. If that happens, the cosmos won't fade into cold silence. It will scream apart atom by atom in a catastrophic finale called the Big Rip. Picture this scenario unfolding over billions of years. At first, the expansion accelerates so gradually that nothing seems amiss. but as the phantom field's influence grows, space itself begins stretching faster than light can traverse it. Galaxies vanish over the horizon, their light never reaching us again. Then, clusters of stars get ripped from their galactic homes. Next, stars themselves are shredded as the space between their atoms expands too rapidly for gravity to hold them together. Finally, in the last milliseconds, even atomic nuclei can't withstand the pull. Protons and neutrons tear apart as the phantom field's grip overwhelms the strong nuclear force. The universe doesn't just end, it unravels. This stands in stark contrast to the more peaceful heat death, where entropy slowly smothers all energy gradients, leaving a cold, uniform void. In that scenario, black holes evaporate over eons, matter decays into radiation, and the cosmos fades into darkness like a dying ember. But the Big Rip is a cosmic executioner, disassembling reality with ruthless efficiency. Why think phantom fields are plausible? Observations of distant supernova already show dark energy's influence increasing over time, though current data doesn't yet confirm the exponential growth needed for a Big Rip. Some quantum field theories predict such behavior naturally, fields with negative kinetic energy that grow denser as space expands, feeding their own destruction. It's like a fire that burns hotter the more you try to smother it. The horrifying beauty of this theory is that it turns dark energy from a passive backdrop into an active player with a will of its own. If true, the fate of the universe isn't just written in the stars, it's encoded in the quantum fields that birth them, waiting to rewrite the rules when we least expect it. Whether the end comes with a whisper or a scream might depend on forces we're only beginning to glimpse. Ever stared at a flickering candle, convinced you could freeze its flame in place if you watched closely enough? That's the essence of the quantum Zeno effect, where the simple act of observation doesn't just reveal reality, but actively alters it. Named after the ancient Greek philosopher Zeno and his paradoxes about motion, this phenomenon suggests that a quantum system constantly measured or observed can't evolve naturally. It's like pressing pause on a video, but instead of a remote, your gaze alone holds the universe in stasis. Here's how it works. In the quantum realm, particles don't have definite states until measured. They exist as probabilities. But every time you check on them, you force a collapse into a specific state. If these observations come rapid fire, the particle doesn't have time to transition elsewhere. It's trapped, frozen in place by the sheer frequency of your attention. Picture a radioactive atom that could decay at any moment. Normally, it'll eventually break down, but bombard it with enough measurements, and you can effectively postpone its decay indefinitely. The watched pot doesn't just seem to never boil. It can't boil, held hostage by the observer's relentless scrutiny. This isn't just theoretical sleight of hand. Labs have demonstrated the effect using trapped ions or photons, where repeated measurements halt their quantum jumps. It's as if reality itself has a performance anxiety. The more you monitor it, the less it dares to change. Some interpretations even suggest that consciousness plays a role, though most physicists argue it's the physical interaction of measurement, not human awareness, that does the locking. Now, here's where it gets thorny for quantum computing. These machines rely on qubits, quantum bits that exploit superposition to perform calculations at unimaginable speeds. But qubits are notoriously delicate. The moment you measure them to read their state, they collapse out of superposition, losing their quantum advantage. The quantum Zeno effect adds another layer. If you monitor qubits too aggressively to stabilize them, you might freeze them so completely they can't perform the very operations they were built for. It's like trying to bake a cake while opening the oven door every second. The heat never gets a chance to work, yet there's a twist. Harnessed carefully, the Zeno effect could actually protect quantum information. Some researchers propose using frequent, gentle nudges to keep qubits in their desired states longer, like a tightrope walker steadying themselves with a pole. The key is balancing observation just enough to suppress unwanted transitions without strangling the system's natural dynamics. From freezing particles in time to threatening the foundations of quantum tech, the Zeno effect blurs the line between witness and participant in reality's unfolding story. It's a reminder that in the quantum world, watching isn't a passive act, it's an intervention, one that can either disrupt or defend the fragile dance of probabilities. Whether a curse or a tool, this effect forces us to confront a profound truth. Sometimes the universe doesn't just unfold, it waits for permission. Black holes were supposed to be the ultimate shredders, cosmic trash compactors where information went to die. When Stephen Hawking first calculated that these gravitational monsters should slowly evaporate, emitting radiation but preserving nothing of what fell in, it sent shockwaves through physics. Quantum mechanics insists information can never be truly lost, yet Hawking's math suggested black holes were the exception, swallowing particles and their histories whole. This contradiction became known as the information paradox, a puzzle so deep it threatened to unravel our understanding of reality itself. But quantum fields might hold the key to this decades-old riddle. Recent breakthroughs suggest black holes don't obliterate information after all. They encode it in ways so subtle we're only beginning to decipher them. Enter soft hair, a tantalizing idea that black hole event horizons aren't smooth, featureless boundaries. Instead, they might be fringed with infinitesimal disturbances in quantum fields, a gentle, low-energy vibrations that act like cosmic fingerprints. Every particle swallowed could leave behind a unique imprint in this hair, etching its information into the fabric of the horizon itself. Think of it like dropping a pebble into a pond. The ripples eventually fade, but the water's surface retains a memory of the disturbance in its subtle molecular motions. Similarly, as matter crosses a black hole's event horizon, it could excite these soft quantum fluctuations, preserving information not in a way we can easily read, but in a form that's fundamentally recoverable. These vibrations wouldn't carry much energy, hence soft, but their patterns might encode everything from a particle's spin to its quantum state. This isn't just theoretical hand-waving. Advanced mathematical frameworks like holographic entanglement entropy show how information could be stored holographically on the horizon's surface. Even Hawking himself revised his stance in later years, proposing that black holes might leak information back out through their radiation, scrambled but not destroyed. Imagine a book burned to ashes classically. It seems gone forever. But if every charred fragment still holds a trace of ink, a powerful enough microscope could theoretically reconstruct the text. Soft hair suggests black holes might work the same way, with quantum fields acting as the microscope. The implications ripple far beyond black holes. If information always finds a way to persist, even in the most extreme environments, it hints at a universe where quantum fields are the ultimate archivists, preserving every event, every interaction in some form. This could reshape theories of the Big Bang, dark matter, even the nature of time itself. The paradox isn't fully solved. Some argue soft hair doesn't account for all the missing information, but it's a profound step toward reconciling gravity and quantum mechanics. From cosmic shredders to celestial librarians, black holes continue to defy expectations, reminding us that even the darkest corners of the universe might still whisper their secrets if we learn how to listen. Plants and birds might seem like unlikely quantum physicists, but nature has been running experiments with quantum fields for billions of years, long before humans ever built a lab. Take photosynthesis, the process that turns sunlight into life. At first glance, it's straightforward. Chlorophyll absorbs photons, electrons get excited, and energy travels to where it's needed. But dig deeper and something bizarre happens. The energy doesn't just bump along randomly like a pinball, it zips through the plant's molecular structure with near-perfect efficiency, as if it's taking every possible path at once. This isn't classical chemistry, It's quantum coherence in action, where energy exists in a superposition, exploring multiple routes simultaneously before settling on the most efficient one. Lab experiments with green sulfur bacteria, some of Earth's oldest organisms, reveal the telltale signs. When scientists blast these bacteria with lasers and track the energy transfer, they catch glimpses of quantum vibrations lasting far longer than room temperature physics should allow. It's as if the molecules are choreographed by an invisible quantum field, guiding energy with precision no human-engineered solar cell can match. Critics once argued quantum effects couldn't survive the warm, wet chaos of living cells, but nature seems to have found loopholes we're only beginning to decode. Now shift from leaves to the skies. Every year, migratory birds like European robins embark on journeys spanning thousands of miles, navigating with pinpoint accuracy using Earth's magnetic field. But here's the mystery: their compass isn't based on metallic minerals like a hiker's. Instead, it's rooted in a protein called cryptochrome found in their eyes. When light hits this protein, it creates entangled electron pairs, quantum twins whose spins are influenced by the planet's magnetic pull. The birds might literally see the magnetic field as a subtle shift in color or brightness, a quantum overlay on their visual world. Lab studies back this up. Fruit flies genetically altered to produce cryptochrome suddenly gain magnetic sensitivity, and artificial systems mimicking the protein structure show the same quantum coherence. Even more startling, these effects persist at biological temperatures, defying expectations that quantum states would instantly collapse in such noisy environments. Some researchers suspect cells have evolved tricks to protect these delicate quantum processes, perhaps using molecular cages or rapid decoherence-recoherence cycles. The implications are staggering. If quantum fields help plants harvest sunlight and birds navigate continents, what else might they be doing? Could our sense of smell rely on quantum vibrations in odor molecules? Might consciousness itself, as some fringe theories suggest, tap into quantum coherence inside neurons? The line between quantum physics and biology is blurring, revealing a world where nature isn't just obeying quantum rules, it's exploiting them, turning the weirdness of fields and entanglement into tools for survival. From chloroplasts to cryptochromes, life's mastery of quantum fields hints at a universe where the boundary between physics and biology is far thinner than we ever imagined. And if nature's been hacking quantum mechanics all along, what other secrets is it keeping? The fabric of our universe might not just be one cosmic tapestry. It could be an endless quilt of realities, each stitched together by invisible quantum threads. This is the mind-bending vision of eternal inflation, where the same quantum fields that birthed our Big Bang are constantly spawning new universes, like bubbles forming in a boiling pot that never stops simmering. Picture an infinite expanse of space, not just vast but exponentially growing, stretching faster than light can cross it. Within this meta-universe, tiny pockets randomly pinch off as their quantum fields settle into stable states, each pocket becoming its own self-contained cosmos with its own laws of physics. Our universe, just one bubble among an infinite froth, riding the crest of an unending wave of creation. The engine behind this cosmic multiplication is the inflaton field, the same primordial force that sent our own universe expanding at breakneck speeds. But unlike a single firework bursting and fading, eternal inflation suggests this field never fully shuts off. Regions where the inflaton's energy remains high keep stretching relentlessly, while pockets where it decays like our universe cool into stable realms. The result is a fractal reality where every decaying patch becomes a new universe and every high-energy region births infinitely more. It's as if you planted a magic seed that grew into a tree, and each of its fruits contained another seed spawning another tree ad infinitum. What's truly staggering is how quantum fluctuations shape these bubble universes. Tiny jitters in the inflattened field determine whether a newborn universe will have 3 dimensions or 30, whether gravity will be strong or weak, even whether matter will outnumber antimatter. Some bubbles might be dead zones where forces cancel out instantly. Others could harbor exotic physics we can't begin to imagine. And because the process never ends, there's no limit to the variety. Somewhere in the meta-universe, there's a bubble where you're a pirate, another where dinosaurs never went extinct, even one where the concept of dinosaurs never existed at all. Critics argue this theory is untestable, a cosmic cop-out that explains everything by proposing infinite possibilities. Yet subtle clues might hide in the cosmic microwave background, anomalies in the afterglow of the Big Bang that hint at collisions with other bubbles in our distant past. Others suggest gravitational wave detectors could one day catch echoes of neighboring universes brushing against our own. And if we're truly living in a multiverse, the very laws of physics we take for granted might just be a lottery ticket drawn at random. One where, by definition, conscious observers like us could only arise in a bubble suited for life. Eternal inflation doesn't just reshape our origin story, it redefines our place in existence. We're not just stardust, we're the accidental heirs to a quantum fluctuation in an unending cosmic chain reaction. Whether a beautiful truth or a dizzying speculation, it forces us to ask, if our universe is just one page in an infinite book, who or what is turning the pages? What if death isn't the end, just a pause in an unfathomably long cosmic story? Enter the Omega Point theory, a radical vision where the far future universe doesn't just fizzle out but becomes a supercomputer so vast it resurrects every consciousness that ever existed. At first glance, it sounds like science fiction, but physicist Frank Tipler grounded this idea in the mathematics of quantum fields and relativistic cosmology. Picture the universe not dying in darkness, but awakening in a final, infinite burst of computation, a moment where quantum fluctuations become the building blocks of eternal rebirth. Tipler's argument hinges on a future where the collapsing universe reaches maximum density, triggering a state of infinite energy and information processing. As space shrinks toward this omega point, the energy density of quantum fields would skyrocket, creating conditions where even the tiniest fluctuations could encode unimaginable complexity. In this extreme environment, every possible configuration of matter and energy, every person, every thought, every moment, could be simulated and recreated with perfect fidelity. It's like taking the quantum foam we discussed earlier and scaling it up to cosmic significance, where the universe's final act isn't an end but a recapitulation of everything it ever contained. The theory borrows from quantum information principles, suggesting that consciousness isn't tied to biological brains but to patterns of information that could, in principle, be reinstantiated. If the universe's final state has infinite computational power, as Tipler argues, then reconstructing every mind that ever lived becomes mathematically inevitable. Your memories, your sense of self, even the precise neural firings that make you might flicker back into existence not as copies, but as continuations woven from the universe's last quantum dances. Here's where it gets theological. Tipler controversially linked this physics to Christian eschatology, framing the omega point as a scientific analog of resurrection. But strip away the theology and the core idea remains startling. Quantum fields might not just shape reality, they could preserve and resurrect it. Critics, of course, pounce on the speculative leaps. The theory assumes a closed universe that collapses contrary to current dark energy observations and handwaves the ethics of simulated consciousness. Even quantum field purists argue that infinite energy states are mathematically treacherous, prone to paradoxes that could derail the whole scenario. Yet the omega point taps into a deeper truth about quantum fields. They're not just actors in the universe's play, they might be its script, its stage, and its final encore. Whether a profound revelation or a poetic mirage, the theory forces us to ask, if the universe remembers, could forgetting ever truly be permanent? From the zero-point field's restless energy to the holographic projection of our entire universe, quantum fields have taken us on a journey where reality is far stranger than fiction. We've explored how emptiness seethes with virtual particles, how entangled particles communicate instantly across cosmic distances, and how the very fabric of space-time might be stitched together by hidden quantum threads. These aren't just abstract ideas, they're radical rewrites of what we thought was possible, suggesting that the universe is less a collection of objects and more a dynamic interplay of invisible fields, constantly shaping existence itself. Think about the implications: the chair you're sitting on, the screen you're staring at, none of it is as solid as it seems. Beneath the surface, quantum fields flicker and dance, blurring the lines between particles and waves, between here and there, between now and then. Some theories even suggest that our entire cosmos could be a simulation running on quantum code, or that we're living in just one bubble in an infinite multiverse where every possible reality plays out. And let's not forget the chilling possibility that the vacuum of space itself might be a house of cards, waiting for a quantum nudge to collapse into a new reality with entirely different laws. So now it's your turn. Which of these theories shattered your understanding of reality the most? Was it the idea that black holes might erase you with a firewall before you even reach the singularity? Or the thought that dark matter could be a shadowy quantum field tugging on galaxies from the shadows? Drop your mind-blown reactions in the comments. We want to hear which cosmic curveball left you staring at the ceiling at 3 in the morning. If you're hungry for more deep dives into the universe's greatest mysteries, make sure to hit that subscribe button. There's always another layer to peel back, another puzzle waiting to be solved. Who knows, maybe the next theory we explore will be the one that changes everything. Until then, keep looking up and keep questioning what's possible. The universe is far weirder than we've been led to believe, and the best discoveries are still ahead of us.